Let's summarize this important relationship between the price elasticity of demand and the revenue function as a function of price. We found that the derivative r prime p is equal to the demand function q of p multiplied by 1 minus the absolute value of the price elasticity of demand evaluated at the particular price. At the price where demand is unit elastic, the absolute value of epsilon equal to 1, then r prime p is 0. When epsilon is precisely minus 1, a small increase or decrease in price will have no effect on the revenue. As long as q is not 0, the opposite is true as well. When the derivative is 0, the absolute value of epsilon must be equal to 1. Demand is inelastic if and only if r prime is strictly positive. At these prices, increasing p will increase revenue. Finally, demand is elastic if and only if r prime p is strictly negative. At these prices, when price is increased, demand will fall by so much that revenue will fall. Let's also summarize the relationship between elasticity and revenue as a function of q. This relationship is even more important. The main result is that the derivative of r with respect to q is equal to the inverse demand function, p of q, times 1 minus 1 over the absolute value of the price elasticity of demand evaluated at this particular quantity. If demand is unit elastic, then r prime q is 0 and vice versa, as long as p is not 0. The derivative of revenue as a function of q is strictly positive if and only if demand is elastic at this quantity, and the derivative is negative if and only if demand is inelastic at this quantity. Note how this is exactly the opposite to the relationship between elasticity and the revenue as a function of price. However, this is not surprising. If demand is elastic, for example, then an increase in quantity will increase revenue. An increase in quantity is associated with a decrease in price, so revenue will increase if we decrease price. This is precisely the same thing as saying that revenue will decrease if we increase price, and the derivative of revenue with respect to price is negative. R prime q is positive while r prime p is negative, since p and q go in opposite directions. Let's do an example of the relationship between elasticity and revenue considering both cases, revenue as a function of price and revenue as a function of quantity. We have seen this demand function before, where this is the inverse demand function. We know that demand is unit elastic when p is equal to 5 and q is equal to 10. It's elastic if p is greater than 5 or q is less than 10, and it's inelastic if p is less than 5 or q is greater than 10. Revenue as a function of p is 20p minus 2p squared. The derivative is 20 minus 4p, and we see that the derivative is 0 if p is equal to 5, precisely when the absolute value of the elasticity is equal to 1. Also, if p is greater than 5 and demand is elastic, then the derivative is negative. R prime p is less than 0 as expected. Revenue as a function of q is 10q minus q squared over 2 with the derivative given by 10 minus q. Again, the derivative is 0 at q equal to 10 when demand is unit elastic. Demand is elastic when q is less than 10, and it's clear that r prime q is positive when demand is elastic. We can also see exactly why revenue is maximized on the middle of a linear demand curve. The first order condition for a maximum is that the derivative is 0, and the derivative r prime q is 0 when epsilon is equal to minus 1. And we know that epsilon is equal to minus 1 exactly at the middle of the demand curve.